This is Lesson 5 in our Calculus 2 series, the number e as a limit. In this lesson, we're going to show how to express e as a limit. We're also going to show how we can use logarithms to compute the limit when both the base and exponent are changing at the same time. We know that for f of x equals ln x, its derivative f prime of x is equal to 1 over x. Then f prime of 1 is equal to 1, and we have 1 equals f prime of 1, and by using the limit definition of the derivative, we can write this as limit as h goes to 0, f of 1 plus h minus f of 1 over h. Now, just changing from h to x, it looks like limit as x goes to 0, f of 1 plus x minus f of 1 over x. So plugging in f of 1 plus x is ln of 1 plus x, and f of 1 is ln of 1, we're here. And remember that ln of 1 is 0, so we simplify to limit as x goes to 0, ln of 1 plus x over x. Instead of dividing by x, we can write this as a multiple of 1 over x, and then bring that up using laws of logs. So now we're here, and we have that 1 is equal to limit as x goes to 0, ln of 1 plus x to the 1 over x. Now we're almost there. Because 1 can be written as this limit, e to the first power must equal e to the power of this limit. So now we have this equation here, and let's simplify the right-hand side. E to the limit as x goes to 0 of ln of 1 plus x to the 1 over x is equal to limit as x goes to 0 e to the ln of 1 plus x to the 1 over x. This is by the continuity of y equals e to the x. Remember that when a function is continuous, you could take the limit before or after you apply the function and you'll get the same answer. So we're here, and now we realize that we have e to the ln of a quantity, so by composition of inverse functions, this is just 1 plus x to the 1 over x. So now we have e is equal to limit as x goes to 0 of 1 plus x to the 1 over x. And so now we have a way to express this number e. Remember that we had defined it to be the number for which the ln function is equal to 1, but now we have a more explicit way to express that. Also notice that if we let n equal 1 over x for positive x values, then as x goes to 0, n is going to infinity. So n is going to infinity, and then x is equal to 1 over n. 1 over x is equal to n. So we can rewrite this limit in terms of n, and it looks like this. Limit as n goes to infinity, 1 plus 1 over n to the n is equal to e. So this is another way that we can express e as a limit. Now notice in both of these limits, the base is changing at the same time that the exponent is changing. The base and the exponent both have an n here, and n is going to infinity. In this case, the base and the exponent both have an x, and x is going to 0. So I often see students confused by this limit because as n goes to infinity, 1 over n goes to 0, so what's inside is going to 1, right? Our base is going to 1. And then as n goes to infinity, this exponent goes to infinity. So I see students often thinking that this should be 1 to infinity, which would be 1 times 1 times 1 times 1 times 1, etc., and that would be equal to 1. But this is not 1 to the infinity because this base is never actually equal to 1. This base is approaching 1 at the same time that the exponent is approaching infinity. So that's why this argument doesn't hold. So whenever you see a variable in the base and a variable in the exponent, we want to take special care when we're computing our limits. And we're going to show towards the end of this lesson how we're going to do that. But now let's take a look at limit as n goes to infinity, 1 plus x over n to the n. Let's take a look at the limit we have here for e, 1 plus 1 over n to the n. Here we have 1 plus x over n to the n. Now we notice, just like with a limit for e, we notice that our base is going to 1 and our exponent is going to infinity. So we think that this might be related to e, but let's see. We're going to start by making a change of variables and letting m equal n over x. So let's see how that changes how our limit is written. Limit as n goes to infinity, 1 plus x over n to the n is equal to limit as n goes to infinity, 1 plus, now this x over n becomes 1 over m with this change of variables, right? Take the reciprocal of both sides. X over n is 1 over m, so that goes here. And n is equal to m times x, so that's in our exponent. So now we're here. But notice that our limit says n going to infinity, but inside we have m's, not n's anymore. So we need to change that. And notice that as n goes to infinity, m also goes to infinity. X is some fixed number, it's not changing here. N is what's changing towards infinity, that makes m go towards infinity and vice versa. So this limit as n goes to infinity is the same as writing limit m goes to infinity. So now we're here. Okay. Now we have 1 plus 1 over m to the mx. If the x wasn't there, we would know that this limit is equal to e. But what is it going to equal with this x in the exponent as well? Let's see. Let's regroup our exponent so we can see 1 plus 1 over m to the m, all taken to the x power. And now notice that m going to infinity doesn't affect this exponent, it only affects the inside. So we can in fact take the limit inside this exponential by the continuity of a to the x, the exponential function. Again, continuity says that we could either take the limit before we apply the function or take the limit after we apply the function and get the same answer. So now we're here, and this limit on the inside we know is equal to e, so our limit is equal to e to the x. Now I don't want you to worry about something like this showing up on an exam. I think it's a bit more difficult than we would put on an exam, but I do think that you should be able to read through and understand all the steps. And we certainly wouldn't have expected you to come up with this idea of changing the variables in order to compute this limit. But once you see something like this, you should keep it in mind for future examples. Let's take a look at another limit with the base and exponent changing. Here we have limit as x goes to 0 from the right, x to the 1 over x. Now again, we have a variable in the base and the same variable in the exponent, and that is the variable that is changing. So we cannot touch this limit, we can't do any computations until we do one thing. We have to apply logs to both sides. By taking the natural log of both sides, that allows us to end up bringing down this exponent and then making computations. So let's take a look at what that looks like. We're asked to find this limit, so we're going to call this limit y. Y is equal to the limit as x goes to 0 from the right of x to the 1 over x. Because we have the variable in the base and the exponent, we're going to take the natural log of both sides. And on the right-hand side, we're going to pull this limit out of the logarithm, again by continuity. So we have the limit as x goes to 0 from the right of ln of x to the 1 over x. And now by laws of logarithms, we can take the 1 over x down in front of the log. So now we're here. Limit as x goes to 0 from the right of 1 over x multiplied by ln x. Now as x goes to 0 from the right, 1 over x goes to positive infinity. What does ln x go towards? Here's our graph of ln x. As x goes to 0 from the right, ln x approaches negative infinity. So here we have a negative infinity, and so the product is negative infinity. So that tells us that ln y, on our left side of this equation, is going towards negative infinity. So what does that tell us about y? Well, let's take this back to exponential notation. E to the negative infinity is equal to y. Notice on the graph of e to the x, as x goes towards negative infinity, e to the x goes to 0. So this limit is 0 and y is equal to 0. And remember, we called our original limit y, so this is the limit that we're looking for. It's 0. And with this, we'll end our lesson on the number e as a limit.